take a photo for attendance purposes here. Let me just, so I can do it later. I can't actually physically do my attendance until 11:30. So I have to kind of have a record of it here. It's ridiculous. So currently, Margot or Kira, if anybody logs in, let me know, okay, please, because I won't notice. Once I have my screen on here. Any questions before we get going? No? All right, I have an amazing curling shot to show you. Any curling fans out there? So that right there, I want to just show it up again, play it again, but cancel that maybe. Does that work? Not used to this. My phone, there's like a replay again. There we go. So for a curling fan, you can recognize that that's an amazing shot. Question is, of course, trying to get to the page here. Question is, was momentum conserved? What do you think? In that crazy shot, pretty complex stuff, right? One stone comes in, hits here, hits there, all this like, you know, boom, boom, lots of interactions. Was momentum conserved? Do you think momentum's conserved or not?
But it always is, isn't it?
You betcha. That's a trick question. So my next question is going to be like, you know, does it depend on whether, you know, like you could think about whether kinetic energy was conserved in there, and that's a maybe and a maybe not. Probably was. The stones are pretty, they rebound pretty efficiently, I think. So I would say kinetic energy was probably mostly conserved in those. They look like they're fairly elastic, but the simpler question here is actually about momentum that I'm asking, right? So the answer is always yes. Right? Momentum is always conserved. So just as a friendly reminder of that, kind of like back in grade 11, we talked about frequency of a wave always is the same as the original, you know, frequency of the source or whatever that created it. And we're gonna actually be talking about that one again very soon. The idea of frequency being the same, as we're going into the light unit after this lesson, which will be today. So conservation of momentum in 2 dimensions, right? In that crazy curling shot, there's a whole bunch of, you know, 2-dimensional angles. It's not just forwards and backwards. So we need to be able to deal with that. Okay, so this is it. Momentum in 2 dimensions. So momentum we know is, of course, a vector quantity. We already know that. But what we haven't been doing yet is breaking that vector into x and y components. Okay, and so we're going to need to do that for this. When we have a 2-dimensional example, we have to deal with the x's and the y's separately. So if I were to load, I'm not going to bother, but if I go back to that original lesson when I showed m1v1 plus m2v2, I pointed out that we're always talking about the x direction stuff, but we didn't really need to talk about it because it was all just x direction stuff. Now we're going to have more than just x direction stuff. So got 10 kilograms, object coming in at 20 meters per second, east 30 degrees north. Determine the object's momentum in the x and y direction. So we're not even talking about collisions yet. We're just reminding you that componentizing vectors is something you need to know how to do. I could, should, whatever, put a square in here. You know, it's obvious that the x and y directions are they have a right angle, 90 degrees between them, right? So let's go with this one next here, I guess. So momentum in the x direction. We look at the x, the blue vector here, and we're thinking, okay, well, we're adjacent to that 30 degrees. So we, in physics, tend to just write out that it's going to be the 200 times what? Anyone?
Cos of 30 degrees.
Cos of 30 degrees, you got it, because we're adjacent, it's cos, so we're good to go, right? I can justify it. It's going to be justified for the other one here. So we'll do that. So you should be able to just jump right to that. Same for this one here. We're looking at the y component and we're opposite the 30. And so for the same, by the same knowledge set, we would say sine of 30 degrees, right? So sine of 30 degrees. And so we just get the answer. If you need a refresher as to where that's coming from, you would just say, oh, well, wait a minute. I can look at this as a right triangle, and I know the opposite and the adjacent and the hypotenuse, and I know, with these two, I'm working with opposite and hypotenuse. So I'm going to use sine and, write down SOHCAHTOA to remember that it's sine and all that stuff, right? But either way, hopefully you can at least get the sine of 30 equals the unknown y component over 200. That, of course, solves to be 200 times the result of the sine 30. Right? And so basically once you've done this, many, many times in a row, you start to notice, you'd be like, oh, okay, the opposite is just, it gives you a little bit of a quick and easy way to get the component, because components are very, very often needed in physics, right? So that's why we think of adjacent as cos and opposite is sine. I'm just going to get my pen here and just make a couple notes on there. So this is obviously adjacent to the angle, and so we're using cos. And over here, let's go with a different color, go green or something. Here we're opposite, and so we're using sine. Right, that's how I want you to be doing it. But short of being able to do that quickly and easily, you do it the long way. So what is the meaning of this? If this object slammed into a north-south barrier, so it's going along, and then all of a sudden there's like a brick wall right here. It's slamming into that brick wall. I won't be able to leave that there because of the covering up other stuff. But if it's slamming into that vertical brick wall, what does that mean? Well, it means that it's going to slam into it, with 173.2, kilogram meters per second of momentum horizontally, and the 100 kilogram meters per second vertically. Right, so it's like how much of a sideways push and how much of a vertical push, right, there is on this object. So if instead of a wall, it was like just another car or something like that, like this, you can picture it's going to be, the momentum's going to come slamming in with a certain amount vertically and a certain amount horizontally, right? So the result of that in a collision and so on. So that's what we're going to analyze the details of to, we have an idea what this would look like. This is how we calculate the specifics, right? So we're looking at, of course, we know momentum's conserved, always, right? So the deal is that we need to do this for, that's what we knew before, right? But now we're going to need to do a little more than that, because of course we're going to have x and y components of this stuff, right? Momentum in the x direction and the y direction are both true. And that's what gives us our starting point for cases like you're going to see here, where we've got, a curling question where we've got multiple angles and so on involved. Okay, so we're going to analyze the x and the y momentum conservation realities. Okay, so you have to work with the x and the y. That's supposed to be an and symbol there. Just noticing. Oh, it looks like there's a spelling mistake. No, maybe not. Momentum conservations. It's just not grammatically common, I guess, or whatever. But momentum conservation, because there's two of them separately. Yeah. So let's do this. We got momentum in the x direction, just like we showed a long time ago. We didn't need the x, but now we do. Momentum in the y direction is conserved as well, so we've got that. All right. And so, same as the one-dimensional work, just more of it. Double the amount, that's all. Okay. Does anybody want me to leave that slide a little bit longer? Or are we good?
Just a minute longer, please. Sorry.
Yeah, no problem. Over there so you can see as much as possible.
Okay, I'm good, thank you.
All right, no problem. Okay, so here's a question. It's got two identical curling stones. They're 19.5 kilograms each. The first stone, call it M1, and hits a secondary stationary stone. M2. So we're going to be listing like M2 equals 19.5. We're going to say like V2 equals 0. And even easier than that, like V2Y and V2X are all 0 as well because it was stationary, right? The first stone's coming in with 5 meters per second north. So if we're choosing a common direction system of, you know, sideways and up, or east and north being positive, basically, then you can say, oh, well, that's all vertical. That's the vertical component, right? So we're going to reason this out and carry out all the numbers. So if the velocity of the first stone ends up being this, so it's at an angle, so we're going to have to think of the x and y components of that, determine the velocity of the second stone. Okay, so you can picture this. I have diagrams coming up here too, whatever, but yeah. So what we're going to be doing is we're going to figure out the x and y components of the final velocity step by step for each one, same as what we've always done, but then the end would be to combine those x and y components to get the actual overall velocity. That's how it works.
Mr. Horn?
Yeah.
After the first stone collides, is the 3.2 meters per second north 30 degrees west, is that from the stationary stone or from its original position?
So it's just the velocity of M1 after the collision. It's always, the reference frame is always the same. It's always just relative to the ice that it's sliding on, or relative to the earth, basically, right?
Okay.
Yeah. So I guess what would this look like here? We'd have the first stone coming in. I was going to do a blue there, so I'm going to switch that up. So we'd have let me just look and see if I have a diagram drawn anywhere. I just forget whether I did show the overall. I don't think it's on here. So I will just draw that as to help visualize things, right? So picture the blue stone coming in hot like this with the 5 north, you know, just roughly speaking. And then it hits red stone. So it's ending up going north 30 degrees west. So it ends up after the collision going like this way, right? So we'll do that better in a second. Just undo those one by one here, apparently. All right, so we're gonna hit red stone. I was just trying to think it through a little bit, but a little bit sort of on the side like that, right? And I'll have to just make that a little bit bigger to keep this realistic because they are the same size. Good enough. All right, so we're going to have a direction system here where it's the one's gonna go off kind of like that, right? So I'll make that be dotted. So north 30 degrees west, maybe it's a little more like that. Make that dotted. So we picture the blue stone going off like that, and we're asking what the other one does. Right, so that's the 3.2, the 30 degrees, and so on, just rough. Anyways, we get the idea that it's going to be going like this, right? But we're just not sure of the details. So got a good visual of it. Now we can start to work our way through everything here. So I think it needs to regain control of the screen here. One sec. Drives me crazy that it does this. I don't know why, but I have to scribble on the screen and then it lets me control the screen. Weird. Anyways, so we've got V1, of course, is the 5 north, and that's just, you know, that's there isn't any x component at all, right? So you could call that V1 y component, really, right? So I'm gonna put in a y component there as well. Let's do that green for that, so we keep with that for the. So that's really a y component because it happens to be perfectly in the y direction. We pick, like I said, the north and the east as your direction system, as we usually would. The 1 is 3.2 north 30 degrees west. So, you know, we can draw that vector and we can calculate its components because we know we're going to need it, right? So if we're looking for the vertical component, actually it looks like I have the horizontal component written first. So notice we're on the opposite side. And so the x component is going to be based on sine of 30, right? like we talked about on the other slide, and then the y component is going to be based on cos. Okay, so just let me jot down some numbers there. I think I can get, that's just conservation of momentum in the x direction, so we can start showing the numbers, how they go into the equation. Of course, we've got our regular m1, v1, and so on. Momentums add up to be the same before and after. And so we can just plug numbers in. So we can put the 19.5 masses everywhere. So you're going to see 19.5, 19.5, 19.5 everywhere, right? We have the no velocity horizontally to begin with. And of course, no velocity at all, either direction to begin with for mass 2. The components before and after are going to start going into here, right? So we've got that 1.6 component. Notice I'm putting it in as a negative. Okay, that's in there on purpose as a negative. Was there a negative here? Not really. It was just, that was our component. We could tell that it was this way, right? But we're putting it as a minus because now that the sign is telling us the direction rather than the picture telling us the direction. Okay, so we have to make sure to put this in as a negative, which of course means left, right? Means, you know, west, I guess. So we have to sort of put that in at that stage of the game there. It doesn't really make sense to put it in down here. Mathematically, you know, down here, the negative's not coming from the sign of 30 or anything. It's coming from the idea that we're recognizing that it's to the west, and we need it to be west relative to the other numbers. Okay, because these ones were east, right? So this one, well, even though they're all zeros, of course. So we have a big old 0 on the one side. We have the result of that multiplied. We're just obviously going to add 31.2 to both sides and divide to solve for v2 prime. Okay, so I could show some of those little math steps in there while you're copying what you need to copy. That's not green. Go ahead and do what you want to do while I just add some of the help here. Right, adding gets rid of that. And then, of course, dividing both sides by 19.5 gets rid of that multiply by 19.5. So nice easy algebra, of course. Same as we've always done. So that's telling us already the final x component of the velocity of the red. So even right now, we start to look at it and be like, notice that this is coming out as a positive here. Right, it became a positive number on its own through the math. We can tell that that kind of agrees with our intuition here, right? I think intuitively we would tell the red stone is going to go off to the right, and so we're getting that positive Vx prime, and we're like, yep, V2x works out. Is there a question there? Okay. All right, so let's keep going. Let me know if you need to go back to that slide.
Use more time, please.
Yep, no problem.
Okay, that's good.
All right. Thanks for letting me know. All right, so we can put some numbers into this y component stuff now too, right? So the second step is going to be working with conservation of momentum in the y direction. So, you know, we know a bunch of values for that. Obviously, the masses are all still 19.5. If we go back to what we looked at here, you can have it all on one page for your work because you're not on a smart notebook maybe, but yeah, we had that y component was 5, right? So we can put that in. The initial velocities of the second one were 0 in both directions, so it's still a 0. Masses are in everywhere, and our y component velocity is in as well. And I'm putting it in as a positive because it was up, right? There's a positive written there, but I'll just emphasize that that was put in as a positive because, of course, it was north, right? So you have to choose, you know, you're in control of the signs, not the math at this stage. Then the math is in control of the signs after that, giving you results, right? So you have to make sure to control those, put those signs in correctly, in other words. Anyways, so multiplying, right? Taking away 54 from both sides, dividing by 19 and a half, and bada boom, bada bing. You've got the vertical momentum value after the collision. I'm just going to squeak that up enough that I can just show a little bit in between here while I'm waiting for copying. Whatever we have as a number there. So we'd have the 19.5 v2y prime, and dividing both sides by 19 and a half again. So what would we have for that? We'd have the 97 and a half, take away the 54, 43 and a half. Okay, so that now we have a vertical and a horizontal component of that velocity. I'm just going to grab a copy of this little diagram. Copy that. Paste that in here somewhere. I'm just going to group those. Just get rid of a little bit of it. Let's get rid of that part. That. And so basically, now we're going to like actually look for V2 prime, right? Well, V2 prime, if you expand this thing to be able to make it better to see, maybe I'll draw this a little bigger. Let me make it so I can do that, right? So this V2 prime has a y component we just calculated there, so I'm going to show the y component here. So this is v2y prime equal to 2.23, and we had previously calculated the v2x prime as, someone might beat me to it here because the computer probably won't let me change my screen. Oh, it is letting me. 1.6. All right, that's 1.6, right? 1.60, I guess, if we had 3 significant digits. I'm not worried at all about what you show for significant digits in your calculations along the way. Like when I did divide by 54.0, I was tempted to just say divide by 54. And this could have been just written as 54 as well, right? You analyze in the end, you go back and you look at what you were given and just keep the correct number of significant digits. If anything, you're going to keep way more digits all the way along in your calculations, right? Like if this happened to be, a non-repeating decimal, which it wouldn't be because it's multiplied, but when you divide stuff, I mean, so this one here, for example, could be a, non-repeating crazy decimal. So you'd show 53.56749 ... Okay. Good at that. So now what do we do to get that overall V2? Of course, you can tell, obviously here, you got a right triangle. And so we're going to use the usual steps from our vector work from grade 11, right? The Pythagorean theorem gives us the length, and tan inverse is going to give us the angle. Easy peasy. So there's the equivalent diagram. Just, that's what I would probably do anyways, right? Actually, is take that diagram and make sure to emphasize what we're doing and get the numbers. So just like going directly to sine or cos for the components, physics people tend to just go right to the root of the sum of the squares for the length. It's actually called the distance formula in math, right? Root of delta x plus squared plus delta y squared. It's your distance formula. So it's not uncommon to use shortcuts like that. So root of the sum of the squares gives us the length, which is our speed value. And then that 54.3 is coming from recognizing that we have opposite and adjacent, so we do tan inverse. So that is the final velocity of the curling stone. Okay. I'm assuming somebody needs to write still, so just let me know when you're done, okay?
I'm done. I don't know about everyone.
I appreciate the volunteering info there. That's good. Okay, right on. So, and it's good. It is good to be saying. I'm sure some people probably aren't writing this down step by step because you have the computer screen, right? But boy, it's good practice, right? If you've done this a few times in the lessons, you go to do it on your own. The homework is going to be less stressful. You're going to be like, oh, I know what to do. I've done this already. My hands already moved that way. Your muscle memory starts to build. So I highly recommend it. So yeah, that's good. If we go back to that amazing curling shot, we maybe can appreciate the idea of it a little bit better, right? We've got all those angles. So each time you see a collision there, those calculations would apply, right? One there, one there, one there. Almost was one there with the one on the in the what's it called? Anyways. All right. So we've talked about different types of collisions before, and so this is a type where you have like energy released. So if you picture something exploding and going off with a whole bunch of different pieces, we're already kind of familiar with the idea that you can have lots of momentum, lots more momentum in individual pieces. But of course, overall, it would add to 0, right? So I am going to assign this one for you to do and submit. Okay, so I had it written as try and then check, but I think I'll put it as I think I'll make this one as an assignment. Okay, so we've got a grenade and blah blah blah. It gives you information. Just realize that we're talking about a grenade that's like sliding along. It's not super realistic, I guess, maybe, right? But it's a grenade that's going to explode out all in a flat 2-dimensional surface. So it could be like it was sliding along ice with its initial velocity, right, along the ground, no friction, and then it explodes into 3 pieces, one going, left and one going right and one going, all these different angles, but they're all still going parallel to the ground. So that makes it a 2-dimensional case, which makes it something that we're ready to tackle. Okay, and there's more examples worked out as part of the homework, of course. So I'll be PDFing and sending that to you. Oh, thank you. Yeah, I'll be PDFing and sending that out, this assignment out, to make sure everybody realizes they've got to do it. All right, so I'll fix that stuff up and send that out once we're done. Any questions?
When would the assignment be due?
Good question. So when I do the email, let's talk about it right now, and then I'll make sure to put it in the email so we don't forget. But would it be reasonable to say you have time to? So there's going to be not as much help sessions these days. So there'd be help session Friday. So I'm going to be really like easygoing and say let's make it due like the end of Monday. And I normally wouldn't make tests on Mondays, but of course you have a chance to get help on Monday anyways, right? So Thursday, actually there might be help available Thursday, Friday. Are you happier with it being longer? I don't want to postpone things too much. What I also have, and I've forgotten to send out the catch-up question, like the uniform motion, uniform acceleration questions, not uniform motion, but uniform acceleration. And there's a catch-up question that I have ready to go. So I'm going to be sending that out as an assignment. Let's make that one due by the end of Friday. Okay, and then the grenade question the end of Monday. Okay, so I'll be emailing those out soon. Maybe a catch-up question due the end of Friday, and a grenade conservation momentum 2-dimensional due end of Monday. So it gives you some time to work things out in that. All right, but yeah, there won't be a help. I won't be able to log in at 1 today, but I will be able to, I think, on Thursday and Friday. All right, so that is, I'm always available by email, of course, but just, can't always do the video sessions or share screen, whatever you want to call it. All right, so that actually is the end of our kinematics dynamics unit, where we tackled energy and momentum and reviewed a bunch of stuff from grade 11 to do with uniform motion, like I mentioned, uniform acceleration, sorry, as I'm saying there's that assignment to do with as well. So switching gears here and starting into the light unit. And so you're going to see a lot of things again here from the grade 10 light unit as a review. Some of it is review, but obviously we're going to be extending, and we have a little bit of a bigger picture, bigger goal in mind with this unit, and it's about the nature of light itself. Okay, so we're going to be looking for the first several days. I want to say 3 or 4 days. We're going to be sort of taking stock of all of the kind of things we know about waves and particles and light. So we're basically trying to figure out, is light a wave or is it a particle? Okay, and we're going to just be constantly looking and concluding in the end, you know, what we've found. So for example, let me just show you like the kind of thing we're talking about here. Like you're gonna see this screen over and over and over again, where we say, well, basically it's light. So light is a particle or wave, and we're as we find new evidence, we're gonna circle particle or wave. I'm not seeing. I don't want to. Yeah, that's fine. I don't want to confuse things there. So let's keep going. You'll see it anyways coming up. Just right here is the kind of thing I'm looking at. So is light made up of a particle or wave? And I'm going to do a screenshot of this over and over again, and we're going to be circling like, oh, based on this new property, this next property we're talking about, oh, that indicates that it's a particle or indicates that it's a wave. Okay, so that's the big picture question we're looking at. And we're also going to end up, you know, reviewing diffraction and refraction and so on and the details of them as we go through it. Okay, because we're looking at those properties to decide if they are evidence of particle nature or wave nature of light. Okay, so the idea here is we have these two different interpretations of light. We could think of light as particles, which are photons, right, which we have already talked about as exchange particles, right, for the electromagnetic field, right? Those are your vector bosons for that that fundamental force, the electromagnetism. And the in the wave theory, we've already talked about electromagnetic waves. So we've actually kind of already talked about all of this, right? But now we're just kind of like looking at it further. So we know light as travels as a, well, we think of light as traveling as a wave through the electromagnetic field, right? But then we also think of it as these particles. So basically, you have to realize that these are scientific models, okay? So they're not necessarily telling you fundamentally what something is. They're just models that help us do what? What are scientific models for? What's going to be when I slide up this screen? The purpose of scientific models is to, any guesses? No. Like science, the whole point of science is to like gain an understanding of things and beyond that to be able to make predictions. Right? So for example, we talk about the idea of electrons orbiting around the nucleus. And then we talked about light, where if the electron absorbs energy, it goes to a higher level. And then as it's going down, it releases that energy. Like it just helps us visualize all of that and make predictions about this kind of thing, or like about what's going to happen, right? So really we're talking about the purpose is, one of them is to help us feel like we understand. Like with the atoms, we feel like, oh, I get it. There's an electron, you know, attracted to the positive nucleus, and so on. We have this like, you know, feeling like we understand things. But is it really what's going on? You know, it's not necessarily true in a literal sense. Like the electrons orbiting like planets do around stars and so on. It's not necessarily literally happening exactly like that, but it still gives us a good feeling of that we understand it. And the bigger thing is it helps us explain observations. So like light being energy being absorbed and light being released, right? We can explain it based on our model. Now explains in quotes there too, because it's again not necessarily exactly what's going on. The big one though that I already talked about was the idea of being able to make predictions. And that's where the models really shine, where it's like you can actually predict new things, and if they turn out to be true, it becomes evidence that your model is true, right? So the one I've been talking about, the planetary model and so on, like I've just leave notes here to do with this, but you know, helps us understand, I feel like we understand what atoms are. It helps explain chemistry, right? With the unstable atoms, because they don't have many electrons in the outer shell. The model helps, you know, us feel like we understand why sodium's reactive and so on. And then you know, like we can make predictions about new materials we discover, right? So you discover a material and you're like, ooh, I'm getting to the category where I'm going to be explosive again. So you're expecting that next atom that you discover or create or find or whatever to be explosive. Like you can make explanations. So this is just relating to your chemistry knowledge. In the model here, you probably have heard through chemistry, you have to start to talk about like quantum nature of reality and so on. And we talked about that a little bit in grade in physics, where we talked about the absorption and emission spectrums and so on, right? How there's specific energies that electrons can absorb, and that all is all part of that model. So that's this stuff here, of course, right? So the way atoms absorb energy is very mechanical. Like it really does behave, and you'll see details of it later on, but it really does behave like light's made up of particles. If you're describing emission and absorption in spectrums, it turns out that particle nature of light is really needed to describe that. And we can't quite get into the details right now, but we will be. And it's when we start looking at the photoelectric effect and the ultraviolet catastrophe are the two key ones that I really, by the end of this course, I'm really hoping you have a good feel for what they mean, why they're historically important, the contributions they made to our understanding of physics. Okay, that's the really, really high-end stuff from this class. Luckily, we're pretty much just going to look at the ideas of it, and then later on, when you look at the math of it in a future physics class, that's when you have like the understanding of what the heck you're talking about as a background, rather than just looking at it as a bunch of numbers that don't mean anything to you. Okay, so that's my goal for this, is to help you understand it at a more fundamental level before you actually tackle the nitty-gritty details of the math. Okay, so I'm trying to help you understand it better than I did when I was learning the math, because it was so much focus just on the calculations that I lost. Actually, you know, like it really did lose sight of what the big picture was. It's only through teaching it over many years that I've really started to understand what the heck I was even calculating. To be honest, it's kind of a sad statement about the university education, that I was able to, you know, succeed, honestly, without necessarily understanding what the photoelectric effect even meant. Anyways, so I want to try and help you get better than that. So historical info, these different models we've had, I'm just going to blast through this. You've heard this lots of times, but well, maybe not actually. But anyway, so the Pythagoreans back in 500 BC thought of light as traveling as fast-moving particles, a stream of fast-moving particles. Empedocles, in around that time, thought that light was traveling like a wave. So even back then, we had these two different ideas, and the debate basically began. So yeah, like we're going way back here, right? It's been wondered about for a while. So we're going to look at different people that supported different ideas and so on, and that. So the Greeks, we had Plato, thinking light consisted of streamers, which are really like your photons, or filaments that they thought were emitted by the eye, which is kind of funny. The eye like shot out a stream of streamers or filaments that would bounce off things, allowing you to see. You know, and of course the like echolocation, like dolphins send out a little pulse and you know, can see, in quotes, but it's quite literally true, right? Dolphins can see using sound, whereas we see using, you know, another kind of physical phenomenon, which is light. Anyways, so the evidence against that model from back in the day with the Greeks was, of course, that you can't see in the dark, right? So why aren't your streamers working when it's dark? It's independent of the human eye, of course. So that's the more historical account of this, you know, but it did start a long time ago. The more recent account of things would be talking about particle versus wave. Newton, like as in Sir Isaac Newton, basically thought it'd be great if all of his laws of motion that he was famous for, right? He was like probably really wealthy and well off and successful because of his Newton's laws working so well. He was really, really well respected. Right? So he wanted his laws of motion to apply to light. So he was hoping, basically, he was very stubborn and insisted, basically, that light was particles. The wave camp was Christian Huygens, which you've heard me mention Huygens wavelets. So that's where that name came from the idea of little circles of waves and so on, combining it. I'll review all of that again. But yeah, basically Newton versus Huygens. And it's kind of funny the way they talk about the history of this. It's like, well, Newton, the bigger name, was supported, like basically this guy Laplace agreed with Newton. And then, Huygens was supported by Robert Hooke. Robert Hooke agreed with Huygens and thought, yeah, I think it's a wave, right? People were trying to decide. Hooke, you probably recognize him from the Hooke's law recently. Okay. So just as a, this isn't for memorization, but if you wanted some extra historical information background, rather, there's Isaac Newton, there's Laplace, Pierre-Simon Laplace, a French physicist. He was posthumously made, posthumous portrait. Anyways, one of these guys became like a duke or something like that. There's Huygens, Dutch mathematician, astronomer, physicist, and there's Robert Hooke. So if you're curious about the human nature of the history of this, those are there as just for interest. Not every single page says, not for memorization. Don't worry, you don't have to memorize this stuff. I'm not going to quiz you on it. It was just for interest. There, it says it on every page now. All right, so the evidence begins here. Okay, so we're going to look at properties of light and basically say, okay, well, can we explain it based on particles or based on waves? The way particles behave or the way waves behave. Remember, that's the big checklist. We're going to go through a bunch of different properties and decide what we think, right? So you see light, for example, traveling in nice straight lines. It's called rectilinear propagation, right? Light travels in nice straight lines. So we look at that and we say, okay, well, is that would Newton and Laplace, Newton and Huygens think of that as like a particle evidence or wave evidence? Okay, so the evidence, of course, is sharp edges, shadows, rays of sunshine. We see it all the time, right? So we know that particles travel through the air in like parabolic paths. Thankfully, due to our previous work to do with projectile motion and all that, right? So at first glance, you might think, okay, well, we don't see light traveling in like parabolic arches, so they might not be particles. But if we notice like faster particles travel straighter and straighter, it kind of led to Newton predicting that light was really fast moving particles. Okay, so 3.0 times 10 to the 8 meters per second fast. So like check is basically, you could look at it as like Newton was right in saying that light is a fast moving particle in terms of that, right? It's like the speed of light is 300 million meters per second. So it's certainly fast. Whether it's a particle or not, I suppose we're still kind of trying to weed that out, right? But you could think of it as it must have a pretty small mass, I guess, right? Because you don't feel light hitting you if it's going that fast. It would have lots of momentum, so it must have a really small mass, if any mass at all. Otherwise, that incredible light speed would hurt you when it hits you. So there's lots of big ideas in this section here that we're just going to think through here, right? So Newton pointed out that waves are very circular, right? They have these curved edges, they radiate in all paths and so on. So that's where Huygens came in and said, oh, well, we can make rays of waves as well. We can have a bunch of Huygens wavelets lined up, and we'd have this wave front that would travel like a beam of light. Certainly each one of these, anyways, I don't know if it's not really talked about as much. Everybody focuses on the wavelets, but even here, it's like right there, that's rectilinear propagation right there, right? So think of rectilinear propagation right there. Like, I don't know what the problem is, right? Certainly, I have no problem thinking of light as a wave based on the fact that it travels in straight lines, right? But I felt he had to convince people of his ideas and what he believed. So he showed this, and then people were like, oh, okay, yeah, I guess it could be a wave after all. So far in our journey here, we were looking at well, we're not really deciding on this page, are we? Right. So this one here, like the or, is kind of left as a big question mark. So basically, we can justify either way. So I don't think we're coming to this one saying, coming from this page saying, oh, okay, I think it's a wave or I think it's a particle. It could be either. Okay. Questions so far? All right. So evidence continued. Let's look at reflection. Basically, like, do particles reflect? Do waves reflect? You know, and of course, you know, particles reflect. So to satisfy the law of reflection, angle of incidence equals angle of reflection, and so on. And Newton just assumed that all of the collisions were perfectly elastic, right? So elastic collisions would do exactly that, and which we've talked about recently. So it's a really nice application of Newton's laws of physics to light, really, right? The idea is like, oh, these collisions are elastic, and so they would do that. And then Huygens pointed out that waves are, you know, observed to reflect directly. So there's no other discussion needed at all. This little applet here would just show the waves coming in and then reflecting out. We've seen it lots of times, right? So it just shows, wow, it's a little complicated looking, but we've got the, you know, the waves coming in and out basically. I don't know why it has to be that complicated looking. We know what we're doing. So, oh, the next step, you can see the Huygens wavelets, I guess. I'll click on it. Object not found, of course. Flash doesn't work anymore. But we get the idea, right? That waves, certainly, we've seen this lots of times. We send waves like this and they reflect out from our own experience in grade 11. So really, the idea of like no extra thought or description needed at all, I kind of feel like this one might be waves winning out, but it's still actually both are pretty good at it, right? So we're not really saying like, ooh, it has to be a particle or a wave yet either, even at this stage, as we're analyzing through different properties. Okay, so you might be just putting a checklist and you're like, okay, well, what about reflection? You'd be like, well, they both can reflect, right? They both do it. So maybe that's what I'll write here. All right, both, right? They both can do it. So basically we're not, maybe that's what I should write too, right? Both can. So it's not really a deciding property yet. Other characteristics of waves, review, and connection to light. So it's all about trying to think of what we know to do with waves, right? So we know waves can be longitudinal or transverse and all that, and they transfer an energy, you know, transfer energy through a material and so on. So let's look at that one. I think this link still works. I checked it recently. Just pause for a second here. You probably couldn't hear that yet, right? I wonder if I can, after the fact, I might just have to plug the microphone in.
I did hear something.
You could hear? When
Yeah, I did.
Did you start the meeting page? Did you say like include computer sound, or maybe we don't need to actually click that anymore? I'll start it playing, and if everybody can hear it. So can you hear the music there, everybody? Anybody not hear it?
I couldn't hear it.
Could not?
No, I can't hear anything anymore.
All right. When you start the meeting, there's apparently I don't know exactly where it is, I forget. When you're starting a recording, or there's a spot you can say like include computer audio. I usually just have been, because I didn't know about it, I was using the microphone. Can you hear me now, by the way, on the microphone? Everybody can, right?
Yeah.
Okay, good. And so anyways, the microphone makes it so you can hear the video. But there's another way as well without the microphone, but I have it, so let's just use it. All right. Hold it slow.
For the sea when waves are mentioned. If you look at the motion of a wave, it appears to be travelling in a definite direction. But does it carry anything with it? You can do an experiment to look at what happens when we generate a wave by dropping a stone in a pond. As the stone hits the water and sinks, it creates a set of circular waves that radiate out from the point of impact. Your waves can move objects in the water or at its edge. To do this, they need to possess energy. So where does this energy come from? Well, some of the kinetic energy the rock has as it hits the pond is converted into energy that is carried away by the waves. So waves carry energy.
Just pause there for quick. When we're thinking of electromagnetic waves, light, if that's indeed what it is, right? You picture like electrons bouncing back and forth and then sending out energy in the electromagnetic field, right? So it's very plausible. Basically, we have ideas that make sense.
Waves also carry water along with them. You see, let's zoom in on the actual surface. Pick out some points to observe. If you look carefully, you'll see that the water actually only moves up and down. It does not travel along with the wave. Waves carry energy without carrying matter. Now let's have a look at our stone dropping experiment again. The wave has to travel to reach an object before it can act upon it, and it takes time to cover this distance. So the wave does carry energy, but only at a certain speed, and this speed depends on what kind of wave it is and what it is travelling through. For example, light is a kind of wave that travels very quickly, and we use it to see the rock or into the water. Sound is also a wave. It travels much slower than light, and we use the sound to hear the splash the rock makes as it hits the water. Both of these waves travel faster than the water wave. This is why we see the rock hit the water slightly before we hear the splash, and why we are aware of both the sight and sound of this before we feel the waves that are produced.
I'm convinced that was a super necessary video, but get to thinking about waves and visualizing and that. Where am I at here? 52. All right. So, we talked before about transverse waves, right? The idea of like the vibration going this way, right? The actual particle is vibrating up and down this way. Right, vibrations that way. And then the actual velocity of the wave is, going with a white marker here by accident. Actual velocity is this way. So they're at 90 degrees to one another. That was our transverse wave stuff we've talked about. Obviously, we know, we got V equals F lambda. It's going to be emphasized more in a second anyways too, but so we have this like V equals F lambda relationship between the speed and so they're noticing here, like you have speed of waves, and then the speed of light is known as this 300 million meters per second. The concept of frequency is referred to in light as well. So frequency and wavelength in light is seen as color. So I'm just trying to make those ties, kind of like when we did the sound unit in grade 11, we talked about how frequency was to do with the pitch, the high and low pitch sound of things, right? So just, I would make note of that. That of course frequency and wavelength are what we see as color. Could just say either of them, frequency or wavelength, because they're fundamentally tied together, because the speed's always 300 million. So we got speed and we have frequency, both of waves and of light. We have a wavelength measurement of light. With light, wavelengths are in the range of hundreds of nanometers, they call it. So for example, I think 670 nanometers, if you're like Google it, let me just undo that M there because it's an N first, 670 nanometers. So that's a nano, which means 10 to the negative 9. That's the kind of length we're talking about. I think that is yellow, if I remember right. But that's, we have wavelengths of light, just like we have wavelengths of waves, and we do our calculations and so on. And so this equation, V equals F lambda, works for light. So maybe just put a star, put V equals F lambda, and V equals F lambda calculations full on, just we do them for light. Now, again, think back to the idea that we're saying, like, with these models, right? If we're using these equations to possibly just model light's behavior, doesn't necessarily mean fundamentally light is a wave or a particle, right? But we certainly know this wave model is working to the point where we can even actually have, the universal wave equation in calculations to do with light. Okay, so all you have to do for this page, I would say, is like speed, frequency, wavelength. exist in very known numbers for waves and for light, and even v equals f lambda, works for light. So this speed here, just make sure it stands out in the notes. I'm saying it's worth repeating and so on, but this fastest known speed, the light is, they always find the speed of light to be 300 million meters per second. In some materials, it slows down, and we'll talk about why when we talk about refraction. Maybe I'll talk about it a little bit now too, because, wow. No. Anyways, yeah, well, a little bit. Light interacts with the atoms or molecules that it's trying to travel through. So instead of light just traveling through a vacuum with no resistance, no delays whatsoever, the energy has to sort of transfer from one molecule to the next through substances, and that slows it down. Yeah, so this is universal wave equation with light. The calculations make sense where you're like, okay, well, the speed's 300 million. We've got a frequency of whatever. So this was given as 100.3 megahertz. Mega means 10 to the 6. So we could write it instead. You could have written it as 1.003 times 10 to the 8 hertz. The mega is just, again, from your metric prefixes. Right? So that's mega, which is 10 to the 6. So look at your metric prefixes from either Google or wherever you have it bookmarked in your work if you ever need it. Yeah, so we have v equals f lambda. Obviously, you can just put in, they rearrange first. We could put in the v and put in the f and just solve for wavelength, right? So I can say or v equals f lambda, the 300 million, 3.00 times 10 to the 8, or just write 3 times 10 to the 8 if you wanted, because we know we're just going to keep the 3 significant digits in the end. Frequency we are given as 1.003 times 10 to the 8, and then we had the wavelength. So, obviously just algebra. Hopefully algebra is your friend. Allows you to get answers. It's coming out as 2.99. What do they do here for random? 3.0078 divided by 1.003 10 to the 8, giving 2.991. I would argue that should have been left as 2.99 if we're keeping 3 significant digits, right? So to me, that's the better one there, 3 significant digits. This number actually comes out as 2.991026 ... So why not keep the 3 if you've started with 3, really, right? So, but whatever. So yeah, that's just showing calculations to do with light, and that'll just give you some practice with v equals f lambda as a review of some grade 11 concepts. Okay, so questions to do with that. This is v equals f lambda with water waves, and then this one is to do with light, where you're basically working with v equals f lambda in both cases, but with a light concept and with a waves concept separately. I'm just doing a quick check here and see if I want to show you or remind you of frequency and so on. Oh, so some things that I should remind you of with this. Couple things. One, I'm going to say a plus reminder or recall or whatever, that the frequency of a wave once created doesn't change. Okay, so frequency of wave once created never changes. And then I suppose we could just remind you of things like, frequency equals number over time. Period equals time over number. Just in case you need any of those calculations and things. Frequency equals f lambda. It's mostly just v equals f lambda. Sometimes they'll give you questions where it's it's not this particular question set actually though, so you might not need those directly. Later on, one that I was working on for a future lesson, they're telling us the wave has this many, has 3, waves in this amount of time, or 3 waves are created in this amount of time, and so on. And so you're calculating frequency as well, but you might not actually need that one. So just that probably needed for this set as a reminder. So it just gets you practicing V equals F lambda stuff. All right. So I do have the refraction stuff left, but maybe that's good for today because we did do the, that these are going to be, there's going to be some calculations involved with that stuff, of course, right? So yeah, I'm going to take a look at my 51 lesson here. There is, yeah, it's not too bad though. Like I end up taking like a full page when I'm doing things, just to spread it all out. But the grenade I'm fitting on 1 page, but the question 2 and 3, I just have them on like 4. They're 1 page each. But yeah, I'm just trying to gauge the amount. I think it's probably appropriate for you to have some time to work on that. So that's it for new stuff for today. Okay. So 51, 52, it can give you some time. By the way, definitely go in and like read over like the things to do with this. When I'm saying reflection, 446, 442, take a look at each of those. You look at reflection with waterways, reflection with light, and so on. Okay, so maybe I'll just before I'm done here saving, I should point out the idea of this, right? So let's go back to this kind of thing here, the evidence and particle and wave and so on. Like when we're looking at, V equals F lambda, etc. I think we're really saying wave for this one, right? V equals F lambda, for light. So when we're gathering evidence here, I think we're saying like, man, it's got some serious waveness to it. If we can do V equals F lambda calculations, just like we did with waves, okay? So, yeah. I will PDF and save and all that stuff. I'll stick around here though for questions if you need, but you're welcome to go and prioritize or whatever you want to call it, decide when you're going to work on things. So it's all good. Yeah. All right.
Oh, sorry. Before you leave, I did see Kira here for a bit.
Oh, okay.
Oh, she's still here.
Excuse me here. Sneezing a bit. Kira is on or not right now? Not right now, though. Did she just leave? Because I was.
I see her here, but.
Oh, do you? Oh yeah.
Yeah.
There we go. Yeah. Okay, good. Thank you for letting me know.
If you're talking about me, I had trouble logging in this morning.
Yeah, fair enough. Yeah, so I did attendance earlier today, Kira, and then I said, let me know if anybody logs in or whatever. So Sarah's just helping me out here. Let me know that you're logged in there. That's good.
Thank you.
Yeah, thank you.
Did you give us the uniform acceleration assignment yet?
No, that's about what I'm gonna get on right now. Okay, I'll send that out by email shortly.
Okie dokie.